let's start this chapter with a new motion diagram. How about of a falling ball? And let's say here at 0 seconds it was just released. And then 1 second later it was here. And then a second after that, when your watch said 2, it was here. And you can tell that the ball is moving faster here because it's covered more distance in that 1 second. And then we're going to lay down a ruler, a coordinate system, so we can talk about its position and know how that changes with time. So we're going to lay our ruler up and down. And when you do that, you really just end up calling it the y direction instead of the x direction, but other than that, there's no real change. So I'll write a little y up here. And now I get to decide where to put the starting point of my ruler. Maybe this is where the hits the ground. Maybe the ground was down here. And we could call that y equals 0. Sure, let's do that. So we could say 0 meters. And this might be, right, and then this might be 1 meter, 2 meters, 3 meters. And because we're going in the positive direction, that's where we wrote our y. Right, it's positive 1 meter, positive 2 meters, positive 3 meters. What we could do with this is turn it into a position versus time graph. Position versus time graph. And here's an important thing that you should just kind of remember all semester, especially when you're dealing with labs, is that whatever is listed first is meant to be on the y-axis. And then whatever's listed second is meant to be on the x-axis. So I'm going to sketch that out. So position, and in this case my position was, we called it y's. We measured it along the y ruler, the y coordinate, and that was in meters. And then time is going to be laid along my x-axis here, and that was measured in seconds. So we can graph it out. At time of 0, it had a position of 3, which is right here. At time of 1, it had a position of 2. And then at a time of 2, it had a position of 0. And if my drawing was perfect, it would have ended up being a nice straight line. So I'll try to fit a straight line on there. This graph is a little bit abstract. So sometimes you have to walk yourself through it a couple of times to really understand it, because it's a lot easier to understand this. Like the ball went straight down. But here what it's saying is as time went on, the ball got to a lower position. It just kind of skews the data. It just shows the data in a different way. One really handy thing about doing it this way is then we could find the slope of this line, and that gives us the velocity. So in this case, the slope, which is rise over run, the rise from initial to final was actually -3. It lost 3. It went downwards. So the rise was -3 meters. And the run, how far did it go in that time along the graph, was 2 seconds. So then the slope here would be -1.5 meters per second. Which, if we were going to, keep going with sig figs, maybe I should round that to -2. So the 2 represents how fast it's going between those 2 points. The negative would indicate backwards against your coordinate system. So if we go back to our coordinate system, we had said counting upwards was going in the positive direction. And that's why we wrote the little y here. So the negative means that its motion was down, or away from our positive direction. Before I scroll more, I'm going to put this in a box. It is important. And if you were just going to write that down on your notes, you should make sure to say that that's on the position versus time graph. So I've sketched out this graph. Let's just talk through what it would mean. An object would start off with a position, a y coordinate of 1, and in the next 1 second, it would have gained a little bit of position and would be even higher now, at a y position of 2. And then for the next 1 second, it stayed at the same height, so it didn't move. And then in the next 1 second, it lost a lot of height and went to a -1. Now before I had said like the origin 0 could have been the ground. Well, in this case it fell into a hole. But here we could also say then that the slope would be rise over run. So there's the rise of +1 and the run of 1 second. So that would give us a slope of 1. And if this was in units of meters, and this was in units of seconds, then that would be 1 meter divided by 1 second. So 1 meter per second. The slope of this segment is 0, flat. So from time 1 to time 2, the object wasn't moving. It had a velocity of 0 meters per second. And then from time 2 to time 3, its slope. The rise was actually a fall, really. It fell down to 3 meters, so we'll say -3 meters. And the run on the graph was 1 second. So from 2 to 3 seconds, its slope was -3 meters per second. So its velocity was -3 meters per second. So one thing you can see on here, that if the slope is positive here, going upwards, that basically means you're going to higher values of your position, higher values on your ruler. A negative slope, a downward slope, means you're going backwards on your ruler. A shallower slope is going to mean slower, and a steeper line would indicate faster. So we have this information now. Let's make a velocity versus time graph. Time in seconds. And this time, instead of position being listed first, velocity is listed first. So we have to write velocity up here. And there's the v. And since we were talking about the velocity in the y direction, we can write a little y down here, just as a little note, velocity in the y direction. Our time was 1, 2, and 3 seconds. And our velocity varied from a +1 to a -3. So +1. Let's look at this segment right here. This whole time, from time 0 to time 1, it had a slope of +1. From time 0 to time 1, it had a velocity of constant +1. And then this isn't really very realistic. It went instantly from a 1 speed and instantly stopped to 0. That's not very physical. Like, it takes you a little bit of time to slow down. But let's just go with it for now. From time 1 to time 2, you had a velocity of 0. So that would be here. And then from time 2 to time 3, you had a velocity of -3 for that whole time interval. For that whole time interval, you had the exact same slope. It just kept it going. If you want, you can connect these with little dashed lines, meaning an instantaneous change. But when you look at a graph like this, it can be kind of confusing at first. So just think of it this way. Velocity of 0 means stopped. And then if you had a velocity of, let's say, -1, it means you were going kind of slow in the negative direction. So I'll say slow in negative direction. And if you had a velocity of -3, it meant you were, faster, but still in the negative direction. And for v of 1, velocity of 1, you're going kind of slow, but in the positive direction. So while you're getting used to velocity versus time graphs, which we tend to use a lot in lab, it helps to kind of think of it this way. If you're going slow or stopped, you're going to be near this axis. If you're going faster, you're going to be farther from the axis here. If you're going faster in the positive direction, or if you're going faster in the negative direction. The last thing to note on this velocity versus time graph is that it indicates our displacement for each of these time intervals from 0 to 1, 1 to 2, and 2 to 3. So if you imagine from 0 to 1, there's this rectangle here. The area of that rectangle would be base times height, but that would be a time times a velocity. So the area of this tells us the displacement. So let's write that down here. The area on a velocity versus time graph gives us the displacement. And it's always going to be the area from this time axis. And so this time interval right here has an area of 0. And this one, its area is below the axis in the negative velocity region. So we're going to actually call that a negative area. I know that feels really weird from math class, but one way you could record that right now would be, this has to be a negative area. It's under the axis. So for this area, the base of it, of that shape, would be 1 second that we read off of that axis, times its height from the axis, which was 1 meter per second. And I forgot to write meters per second here. I should go back and do that. And then you have a second in the numerator, and then a per second over here in the denominator. So those cancel out. So you end up with 1 meter. So that's a plus 1 meter. Here it didn't change its position at all, displacement of 0. And here for this area, I'll do it this way. Its base was 1 second long. So do 1 second times its height, but its height was below the axis at -3. So we'll say its height was -3 meters per second. And that way it'll give us a negative area. So -3 meters, because a second in the numerator, we'll cancel out with a second in the denominator. So from 2 to 3 seconds, it lost 3 meters of height, which we should be able to go back up and see. From 2 to 3 seconds, it lost 3 meters of height.